Hi folks, we're going to take a look at number 17 on page 269. So here it tells us that a farmer has 750 meters of fencing, so wants to enclose a rectangular area on all four sides and then divide it into 4 pens of equal size with the fencing parallel to one side of the rectangle. Okay, so let's start with a diagram, and then let's see what they're looking for. They're looking for the largest possible area of each of the 4 pens. Okay, so it looks like they're looking for the areas or maximum areas for the individual pens. Okay, but of course these pens are all the same size. So we have some rectangle. It's going to be fenced on all 4 sides, and then we're going to take this and split it up into 4. Okay, so we've got something that looks like this. Okay, and they want the maximum area for any one of these individual pens, and the constraint that we have is that we can only use we have to use exactly 750 meters of fencing. Okay, so in terms of what I label as a variable, since I'm looking for the area of one of these individual pens, I might as well call this little bit x, and then that'll be y. Okay, instead of calling this whole side length x, could have done that too. All right, and let's come up with an equation that we want to optimize, and what we want to optimize is the area of one of these individual pens. So what we want to optimize is a equals x times y. Nice simple function, but it's got that problem that we often run into, is that it's a function of 2 variables, so we need to write this as a function of 1 variable, and this is where the constraint is going to come in. It tells us that we have to use 750 meters of fencing. So the fencing is going not just all the way around, but also breaking these up into 4 equal pens. So what I have is that the 750 meters, let's see how it's distributed. Well, I'm going to have 1, 2, 3, 4, 5, 6, 7, 8 of these x lengths to cover the top and bottom, and then I'm going to have 1, 2, 3, 4, 5 of these y lengths on either end, and to split it up into 4. Okay, so we can say that 750 is going to be equal to 8x plus 5y. All right. So now what I can do is I can use this equation to write one variable in terms of the other, and then do a substitution. And what that will leave me with is a single variable that I can, in my function, that I can then optimize. Okay, so here, I mean, neither of these are great. I guess I'll isolate y, so at least I'll be dividing the 750 by 5. Okay, so here we've got y is equal to, it's going to be negative 8x plus 750 all over 5, and let's, so 8 over 5 is like 16 over 10, so it's going to be 1.6, so negative 1.6x, and then 750 divided by 5, also 75 divided by 5 is 15, so plus 150. All right. So now that I have y written in terms of x, I can now rewrite my area function as x times negative 1.6x plus 150. And this is the function that I'm going to be optimizing. Now, a very easy one to optimize because, it's just a quadratic. Okay, so it won't be too much work to do here, but let's go ahead and do that. Okay, so let me start by simplifying here. So negative 1.6x squared plus 150x. All right, and of course I'm going to find my optimal values. Now, one thing notice here is that they don't give us any constraints on the individual lengths. Okay, so I'm just working with any possible values of x or y, which of course would mean that they just need to be positive. All right, so let's take the derivative here. A prime is 1.6 times 2, so negative 3.2 x plus 150. And of course, we want to set that equal to 0. Okay, so let's determine our critical number. So x is going to be equal to, so bring that over to the other side, so 150 divided by 3.2. So 150 divided by 3.2 is 46.875. 46.875. All right. Now, this is one of these scenarios. Normally, I would say, well, you need to check that this critical number actually relates to a local, in this case here, maximum, because we're looking for largest possible area. We don't actually have to do that here because quadratics are functions that we know very well. So we know that this is going to be a max since it's a quadratic, okay, with a greater than, a less than 0, okay? So we know that a quadratic function whose leading term is less than 0 opens downwards, hence we know it's a maximum. Okay. Had this been a cubic function or any other function, remember that the expectation is that you're actually showing that it's an extremity at that value. Okay. So let's go back and see what they're actually asking us for, because this just gives us this x value, which produces a maximum. Let's go back to the question. It says, what is the largest possible area? So what we're actually looking for is the area of each of the 4 pens, okay? And of course, this function here represents the area of one of those pens. So I don't even have to find the y value. I could just stick this x value into that equation. Negative 1.6 times 46.875 squared plus 150 times 46.875 equals, all right, let's bring that here. So negative 1.6 times 46.875 squared, okay, and then plus 150 times 46.875, and that gives us 3515.6. So 3515.6, and we're dealing in meters, so this is going to be meters squared. All right. So let's just recap. So step number 1, get yourself a good diagram to kind of place yourself in the problem. Step number 2, figure out what you're trying to optimize. In this case here was the area of one of these individual pens. Okay, 2 variables, so that means you're going to have to try to write these variables in terms of one variable. In this case here, using this fencing information, all right, and how many pieces of each I need, I was able to write y in terms of x. Okay, this would have worked if I wrote x in terms of y, do my substitution, and then I'm left with a function of one variable. And that's where now I can do my calculus algorithm, which is to take the derivative, find the critical numbers, determine whether that critical number matches the information you're looking for. In this case here, a largest possible value for the area, which it does. And then from there, make sure you answer the specific question. All right, that is it for this one.